Okay, so I would like to continue with lecture. And in order to do so, I just want to quickly recap the properties of R, the set of real numbers that we've talked about so far. We've talked about how R is complete and in two different senses. One is the least upper bound in the sense of least upper bounds, and the second is in terms of Cauchy sequences, right? So Cauchy sequences are convergent, and the least upper bound property states that if you have a non-empty subset of R, which is bounded above, then there exists a supremum of that set, which is a real number. Um, I wanted to mention this. We also have, just like we have the least upper bound property, we also have the greatest lower bound property. Okay, so we focused on and we gave the definition of supremum, but you also have infimum. So you have the definition. You can have an infimum or the infimum of a set. Okay. So I encourage you to go back. This is mentioned in the textbook. Go back and rework the definitions and the proofs for infimum and greatest lower bounds, right? So what would the greatest lower bound property be if you have a non-empty set which is bounded below? Then that set has an infimum, a greatest lower bound, right? So you can go back and redo the proof, but modify it to kind of work with this analogous case. Okay. The second, let's see here. We also talked about how R is an ordered field, and so that was very um, that was discussed in great detail in the textbook. You can go crazy with that. I'm going to get all into that, the properties of fields. Now, in that section, again, everything is done in terms of Dedekind cuts. We are not focusing on, we are going to assume that the real numbers have been constructed and do exist. So if you're interested in the Dedekind cuts, then read that, right? Have fun with it. If you're not all that interested, feel free to pass over it. And as you're reading about how R is an ordered field, um, you can essentially ignore the part about cuts and just think of real numbers, right? And then the next thing is triangle inequality. This is really, really helpful. We've already used it a few times in proofs. Triangle inequality is really helpful in proofs because it helps us to estimate. Okay, I want to introduce a new property. New property is called the Archimedean Property. The Archimedean Property says that for any two real numbers, if they're greater than 0, there is an integer, a counting number n, such that n times a is bigger than b. Now let's look at this practically speaking. What does this mean for us? Let's consider the case where a is strictly bigger than b. Now, I'm going to draw a little line segment here. And I didn't mean to use my marker, but whatever. So we're in a situation here where here's 0. So a and b are both greater than 0, and a is bigger than b. Okay, in this case, there's really nothing to prove because you just let n equal 1. If you let n equal 1, then it will be true that there exists an n, right, a counting number n, such that n times a is bigger than b. Okay, now what about if a is equal to b? Well, now here, if we were to do our same little number line, here's 0. Now a and b are the same number. What should we choose for n? Well, you could choose n equals 2, or you could choose n equals 3, right? Then a times n will be bigger than b, okay? So the real meat of the proof comes in dealing with the case where where a is less than b. And so the idea is here's 0, and if a is here and b is all the way here, we have to show that we can have a bunch of copies of a. It's like here's 2a, 3a, 4a, And it might take you a long time, so you might have a large value of n, but at some point you will have a multiple of a which is larger than b, an integral multiple, an integer multiple of a larger than b. Okay, so the proof of the Archimedean property, I actually have the proof in a YouTube video, and I have posted the link in the announcements. So I'll just put here proof on YouTube. So, and again, I've given you the link to the proof in the announcements and B courses. Now, the Archimedean property is used to prove the next property, the next important property of R, which is that Q, the set of rational numbers, is dense in R. What does it mean to say that Q is dense in R? It means that every interval in R, so let's be specific here, every interval in R, no matter how small, contains a rational number. So in between any two real numbers, there's going to be a rational number. We also have that the irrationals are dense in R. So between any two numbers, real numbers, regardless of how small they are, there's an irrational number as well. So every interval, no matter how small, contains an irrational number. The proof that Q is dense in R, so this proof is also on YouTube, and the link is in the announcements in B courses, right? And as I said before, it relies on the Archimedean property. Now, the proof that the irrationals are dense in R, this proof is actually going to be part of your homework set. Proof for problem set 2. And I'll put a smiley face because that should be pretty fun. When you're doing this proof, so I've included a hint in the problem set, assume that you know that Q is dense in R, right? So prove this one prove that the irrationals are dense in R after you've proven, or after you watch the video and take notes on the video showing that Q is dense in R. Okay. So again, we're just going through properties, principles of our tools that we'll use and abuse. Just kidding. No, we'll only use these tools. Let's see here. Next thing on our list, the Epsilon Principle. Epsilon Principle is really, really cool because epsilon usually refers to a small positive number. Anytime you're restricting your domain to positive numbers, good chance you're working with distance, right? So we'll use Epsilon Principle a lot because it'll allow us to approximate or translate our proofs by looking at them in terms of distances. Okay, so let's read here. So we're saying, suppose you've got two real numbers, A and B. The first principle says that if for every positive value of epsilon, so if A is less than or equal to B plus epsilon for every positive value of epsilon, then A is less than or equal to B. The second statement is that if for every epsilon greater than 0, the distance between A and B is less than or equal to epsilon, then A is equal to B. Okay, so let's look at how to prove. Oh wait, so let's prove that the irrationals are dense in R. Oh yeah, this is going to be on your homework. So problem set 2 for you. Okay, let's prove the epsilon principles. So the first one was we'll have our hypothesis. The first one said that if you have real numbers A and B, if for every epsilon greater than 0, A is less than or equal to B plus epsilon, then A is less than or equal to B. For hypothesis, we're going to say let A and B belong to R, and suppose that for every epsilon greater than 0, A is less than or equal to B plus epsilon. That's the hypothesis. The claim is that A is actually less than or equal to B. Now over here, we'll do our sketch work. And for our sketch work, here's the idea. Here's A. And we're saying that for every epsilon, A is less than or equal to B plus epsilon. And we're supposed to conclude that A is less than or equal to B. So imagine if it's not the case that A is less than or equal to B. That would mean that A is greater than B. Now, can this happen? This is what we're asking ourselves. If this can happen, we'll get a contradiction because we could have an epsilon where A isn't less than or equal to B plus epsilon. Do you see what I'm doing there? What's the epsilon I would use? I could use epsilon to be half the distance between A and B. Does that make sense? So if I let epsilon be half the distance between A and B, then I would get a contradiction to the fact that for every epsilon greater than 0, A is less than or equal to B plus epsilon. Okay, so let's go ahead and formally write our proof. So we're going to do a proof by contradiction. Suppose not. Then A is strictly bigger than B, right? Let epsilon equal A minus B over 2. This is going to be the distance between A and B over 2, half of the distance between A and B, right? That's why we're choosing that epsilon. And now we're going to say epsilon is greater than 0. Why is epsilon greater than 0? Since A is bigger than B. So, according to our hypothesis, A is less than or equal to B plus epsilon. But what is B plus epsilon? B plus A minus B over 2, right? So we've got A is less than or equal to B plus A minus B over 2. Multiply everything by 2, which is okay. 2A is less than or equal to 2B plus A minus B. 2B minus B, that's B. So 2A is less than or equal to B plus A. Subtract A. And we'll have A is less than or equal to B. Contradiction. So this contradicts A greater than B. So we're done with our proof, and we can conclude that A must be less than or equal to B. Does that make sense? Okay, let's add a page afterwards. And now let's prove the second epsilon principle. So the second epsilon principle had as hypothesis that A and B are real numbers, and for every epsilon greater than 0, the distance between A and B is less than or equal to epsilon. The claim is that A must be equal to B. All right, so for our proof, again, we're going to do a proof by contradiction. Suppose not. So if A is not equal to B, that means that the distance between A and B is bigger than 0, right? Again, we're going to let epsilon equal the distance between A and B over 2, so that epsilon is bigger than 0. That's good because now, by hypothesis, since epsilon is greater than 0, for this choice of epsilon, the distance between A and B has to be less than or equal to epsilon. But now, what does this imply? This implies that the distance between A and B is equal to 0, right? If we multiply both sides, sorry, it's bigger than or equal to 0. Let me just go ahead and do it. Cross multiply, so we had 2 times this distance is less than or equal to the distance, subtract 0 greater than or equal to here. We get a contradiction because up here we said that the distance between A and B was strictly positive. So it must be that A is equal to B. And we're done. Okay, I want to talk a little bit about Euclidean space. Now, we've been working with Euclidean space, with specific Euclidean spaces for a while now. Not in this course, but just in our mathematical careers. But for the sake of completion, no pun intended, I'm going to go ahead and just lay out some small facts here. And this is, again, just an introduction to Euclidean space. It'll be a very key, a rich source of examples and counterexamples as we move on to Chapter 2, Topology. So we want to get it in now while we're laying our foundations, right, in Chapter 1. Okay, so what do we consider Euclidean space? It's another way to say Rm, where m is any index on natural numbers. And we're expecting, why is it called Euclidean? Because we have the way we measure things is generalization of how we measure in R, okay? So in fact, we will have distance with absolute values in Rm, the same as we do in R. So formally, it's just a Cartesian product of m copies. And let's see here, let me try to get my little. Right, so notice that these are m copies of R. We call the real numbers, so if m is equal to 1, then the elements of Rm are called scalars. If m is greater than 1, then we call these elements vectors, okay? And everyone has had multivariable calculus, so you're used to, and you've seen this at least in 3 dimensions. So you've worked with m equals 3, m equals 2, and m equals 1. And we've got well-defined operations in Rm in Euclidean space, adding and subtracting. Now, that's just coordinate-wise, right? And so we know what that means. So if you want to add 2 vectors, you just add each coordinate of the vector. What do we mean by coordinate? That is this would be the location of the first coordinate, location of the second coordinate, all the way up to the location of the nth coordinate. So it's a way for us to describe the different parts of our vectors. Scaling is a way of saying that you're going to multiply a scalar, which is a real number, times a vector. So we are able to do that. And just as an example, so say C belongs to R, so C is a scalar, and X belongs to Rm, so X is a vector. then Cx means Cx1, Cx2, all the way up to Cxm. Right, so this is if x looks like x1 all the way up to xm. So to scale a vector, you just multiply each of the components by that factor. Now, we have a way to multiply a vector by another vector. Now, the key here is that these vectors have to both be within the same Euclidean space. So both in Rm. And it is the Euclidean dot product. So suppose x is equal to x1 all the way up to xm, and y is another vector, y1 all the way up to ym, then the dot product of them would just be the sum of what you get when you multiply the components. Okay, so this is the formula for the dot product. And again, you saw that back when m equals 3. Next thing is Euclidean length. Now, how do we define length? Well, the length of a vector is going to be the square root of what you get when you dot a vector with itself. Right? So it's going to be the square root of the xi squared, 1 to m. Now, in the case that m equals 2, well, never mind. We'll get to that. Okay. Well, I can say that quickly. In the case of m equals 2, this is just the Pythagorean theorem. Okay. So you can think this is just quickly here. If you have a vector and this is x1 and this is x2, then the length of the vector is the length of the hypotenuse, which is the square root of x squared plus x1 squared plus x2 squared. Okay. And now what's the distance between two vectors in Rm? So I'm going to borrow this notation from up here for my dot product. So I'm assuming that here we go. So here we go. I'm assuming that x and y are vectors in Rm, and the distance between them, which would be denoted like this. So we use those same absolute value bars, and then just absolute value of x minus y. But it's not absolute value, it's the distance, right? It's the Euclidean distance that is defined to be the length of the vector that you get when you dot x minus y with itself. Okay, so that ends up being the square root of the sum of xi minus yi squared. And so notation for length of x, let's go back in and put this in. It's also called the norm of x because it's a norm. We don't need to get into that, but just mentioning it. I think maybe the book gets into it. Okay, so most of that stuff should be somewhat familiar, especially when m equals 3. And let's practice with the following definitions. Now, a box. A box is taking closed intervals and taking the Cartesian products of closed intervals in Rm. So let's look. What is the unit cube in R? So the unit cube in R would just be from 0 to 1, right? And we know what that would look like. in R, we would just be looking at a closed line segment, right? It doesn't look like a cube that much, but it's what it is. Now, what about in R2? In R2, we're talking about 0, 1 cross 0, 1, and that looks like it's a square, right? When do we actually get a cube shape? It's not until R3. Here, we get a genuine, a decent cube going. Let's see how my drawing skills are. Not too bad. Yeah, so that would be the unit cube. Very similar to unit ball. Now for us, unit ball, and this is a typo in the book, I think. Unit ball, the open ball, is going to consist of all of the points. Open ball that's centered at X with a radius R greater than 0 is a set that consists of all of the points in Rm that are within R units, or that are less than R units away from X, right? So unit ball, what does the unit ball? Now, unit ball means we are now going to be centered at the origin, and R is equal to 1. So let's put this here. So centered at the origin, and R is equal to 1. So the radius is equal to 1. Now let's see here. In R, that will look like the open interval from -1 to 1. In R2, we're looking at the open unit disk. And then in R3 is where we actually get a ball. We get a three-dimensional object. Okay. Let's go to give one more definition of the sphere. Essentially, the sphere is going to be the boundary of the ball, right? So the sphere is now going to be, that's centered at X, radius R, is going to be the set of points in Rm that are exactly R units away from X. So now unit ball, again, X is going to be the origin, and R is equal to 1. So what is the unit ball, the unit sphere when M equals 1? It's just going to be a set of endpoints. Right? Because you're literally solving the equation absolute value of X equals 1. And so X is plus or minus 1. Okay? What about when M equals 2? Now, we've got the unit circle. So it's just the edge, right? It's just the border, not the points inside. Unit circle. And then for unit 3, it's the unit sphere, just the boundary there. Now, notation. So Sm minus 1 is an m minus 1 dimensional surface in Rm. So, for example, S1 is a one-dimensional surface in R2. So S1 is a unit circle. Why is it one dimension? Because the unit circle is determined completely by theta, right? You change theta, theta ranges from 0 to 2 pi, and all I need to know is one dimension. I just need one piece of information, theta, and I know my location on the unit circle, right? So you'll have one less, the dimension will be one less than m, because when you solve this equation here, you'll have um, like one of, when you solve it, you'll have m minus 1 free variables, okay? All right. So I believe that is all I wanted to say about Euclidean space. And the last thing I wanted to do was to just give a brief, get us ready to talk about cardinality by going over these definitions. Function. What's a function? It's a mapping, transformation. So a function, also called a map or transformation. A mapping, several different versions depending on the course, right? Depending on the subject matter. That sends elements from one set, the domain, to another set, the codomain, or this is also called the target. I think the textbook uses the vocabulary word target, okay? In terms of notation, we just have a little f to represent the function, semicolon, and then our domain, a long arrow, and then the codomain, okay? And then below here, I've written in blue that A maps to, so A maps to f of A, means the image of A under f is f of A. So here, f of A is the element in B. Right? And A belongs to our domain A. Now let's, just for the record, we're going to define the range. What is the range of a function? The range is the set of points that are in the that are the image of points in the domain. So we have it right here. So there's a set of B in our codomain such that there exists an A in our domain satisfying f of A is equal to B. So sometimes students confuse the range with the codomain. Sometimes the range and codomain are the same thing, but oftentimes they are not. Okay? Now, injective. What does injective mean? Injective, that's also known as one-to-one. Right? For every, so whenever you have A and A prime, if you have two elements in A in your domain, right, f of A is equal to f of A prime only when A is equal to A prime, right? And we actually could make that an if and only if, because obviously if A is the same thing as A prime, then f of A is equal to f of A prime, right? Because that would mean that the function is well defined, right? So one point isn't mapped to two different distinct points in the codomain. Surjective, another way to say surjective is onto. And that just means that every point in your codomain is in the range. So the range is equal to the codomain. And then, of course, bijective means you are surjective and injective. And in terms of quantifiers, we would say for every B in B, there exists a unique A in A such that B is f of A. Okay, so notice that sometimes I'll put the parentheses, but sometimes I won't. And usually I won't, actually. All right, and that leads us to cardinality. What is cardinality? Suppose you have two sets. If f is a function from A to B and f is a bijection, then we say that A and B have the same cardinality. So cardinality is the size of a set in some sense. Okay. Notation-wise, we might write that A and B have the same cardinality using this notation, or right, that A and B have the same cardinality using the absolute value notation, right? Now this hints at the fact that cardinality is having the same cardinality is an equivalence relation. Okay, we'll talk about that a little bit more on Tuesday. The last little bit of notation that I want to introduce is this notation here for the finite set that's just 1, 2, 3, all the way up to n. Here's our notation for it. So how do we know a set is finite? A set is going to be finite if there exists an n, a little n, such that the set has the same cardinality as n. That's the definition of A being finite. Okay? All right. So the last thing I wanted to do was talk a little bit about the exam that's going to be next Thursday. So I came up with this list, and essentially my approach for exams is to have them shorter rather than longer. So expect the exam to be 1 hour long, and also the exams will be all the questions are questions that I'm expecting you to answer, right? The exam's strictly timed. So exam's 1 hour, everyone gets the same amount of time. And you just have to submit the exam. You know, the questions are made to be answered within a very specific amount of time. Okay, no calculators will be needed. No cell phones will be allowed. No headphones. None of that. All right. Other things you can skip is /omit. Dedekind cuts, I think that's in section 2. And Cauchy-Schwarz inequality, convexity, inner product spaces. I think that's maybe in section 1.3. And the proof of Schroeder-Bernstein, which is 5, I think that's in 5-star, section 5-star. However, for emphasis, I do, and we'll talk about the Schroeder-Bernstein theorem, but you want to know the statement of it and be able to use it because it's really helpful for cardinality. Of course, you want to know your definitions, the statements of your theorems. Make sure that you know how to determine the hypothesis and the claim, right? Because that can still be kind of tricky. I'm going to expect you to provide formal proofs on the exams, okay? Make sure that you look over the notes that I sent in the announcement, the links. It's like 2 or 3 different notes, right? Make sure that you're familiar with them. They summarize and all say kind of the same thing, but it's just prerequisite information about logic, and that's you're expected to have studied that stuff, or if you don't already know it. Of course, to emphasize least upper bound property, triangle inequality, supremums, infimums. I think you get some more practice with that this week. Also, max and min, upper bound, lower bound, right? These are all embedded in the definition of supremum and infimum. Cauchy sequences, convergent sequences. We spend a lot of time negating them, considering the implications of a sequence not being convergent, a sequence not being Cauchy, right? So make sure you're comfortable with them. The Cauchy convergence criterion for sequences. Took us a long time to prove this today in class because we had to give a super long proof that R was Cauchy complete, meaning Cauchy sequences converge. Then we've got the Archimedean Principle that comes in handy. The density of Q and irrational numbers in R. The Epsilon Principle, we'll use it all the time. And then when we get to cardinality, as I said, we gave just a brief intro. We'll talk a little bit more about that, different sizes, denumerable, countable, uncountable, etc. So yeah, make sure that you know your definitions, right? And make sure that you know your statements of theorems. Okay. For super long proofs, you're not expected to recreate a proof that takes 45 minutes in class for me to write. Think about it. If the exam is 1 hour long, and if I have 4 or 5 questions on the exam, that means that no question should take more than 20 minutes, right? So even if there are some short questions, like the longest question should take you like maybe 20 minutes. Okay. Okay. All right. That is all for now, and I'll see you in class on Tuesday. Thank you.